Welcome to an example on how to evaluate a flux integral when the surface S is given parametrically. We want to evaluate the double integral over the surface S of f dot differential S, where the vector field F is given here, and the surface S is the helicoid with the vector equation given by r of u comma v. U is on the closed interval from 0 to 2, and v is on the closed interval from 0 to pi with an upward orientation. So a flux integral is normally given in one of these two forms here on the left, where if the vector field F represents a velocity field of a fluid flow, the flux integral represents the volume of fluid flow across the surface S. The units would be volume per unit of time. So if S is the oriented surface given by r of u comma v, and r is the region in the UV plane, so r is the projection of S onto the UV plane, then we can evaluate a flux integral by evaluating this double integral here on the far right over the region R. So the flux integral is equal to the double integral over the region R on the UV plane of f dot the partial derivative of r with respect to u crossed with the partial derivative of r with respect to v differential A, where differential A would be equal to du dv or dv du. So going back to our problem, before we set this up, let's look at this graphically. So the surface S is graphed here in green, and the vector field F is graphed in gray. If we look down on the UV plane, we can see the region R is this half circle or semicircle, and the value of the flux integral is going to be the flow across the surface in volume per unit of time. And because the orientation is upward, we can see the value of the flux integral is going to be positive. So going back to our work, again we're going to set this up as a double integral over the region R, but the first thing we need to do is write the vector field F as a function of u and v, since differential A is equal to du dv or dv du. So looking at r of u comma v, notice how x equals u cosine v, y equals u sine v, and z equals v. So the vector field F of u comma v has an x component that's equal to y. So the x component would be u sine v. The y component is negative x, and therefore the y component is going to be negative u cosine v. And the z component is z cubed, which would be v cubed. And now let's determine the partial derivatives of r with respect to u and v. So the partial of r with respect to u would have an x component that's a derivative of u cosine v with respect to u, which would be cosine v. The y component would be the derivative of u sine v with respect to u, which would be sine v. And the z component would be the derivative of v with respect to u, which would be 0. And now for the partial with respect to v, the x component would be the derivative of u cosine v with respect to v, which would be u times negative sine v, or negative u sine v. The y component would be the derivative of u sine v with respect to v, which would be u cosine v. And the z component would be the derivative of v with respect to v, which is 1. Now let's go ahead and find the cross product, and we'll set this up as a 3 by 3 determinant. So to determine the cross product, the first row are the unit vectors I, j, and k. The second row are the components of the partial with respect to u. The third row are the components of the partial of r with respect to v. And now using expansion by minors, to determine this first 2 by 2 determinant, we eliminate the row 1 column of the I vector. So we eliminate row 1, column 1. These four elements make up this first 2 by 2 determinant times I, and then we have minus. For the next 2 by 2 determinant, we eliminate the row 1 column of the j vector. So the remaining elements make up the second 2 by 2 determinant. And then for the last 2 by 2 determinant, we eliminate the row 1 column of the k vector. So we eliminate row 1, column 3, which gives us these four elements. And now for each 2 by 2 determinant, we're going to find this product minus this product. So here we have sine v times 1 minus 0, so we have sine v times I, and then minus cosine v times 1 minus 0, so we have minus cosine v times j. And here we have u cosine squared v minus negative u sine squared v, which gives us u cosine squared v plus u sine squared v times k. But notice how here, if we factor out u, we'd have u times the quantity cosine squared v plus sine squared v. We should recognize this identity. This simplifies to u times 1, and therefore the components of the cross product are angle bracket sine v, comma, negative cosine v, comma, u. So going back to our first slide, we now know the cross product of these partial derivatives would have components sine v, comma, negative cosine v, comma, u. So the given flux integral is equal to the double integral over the region R. Remember, the region R is S projected onto the UV plane, which would be this region here. And then we have f of u comma v, which we have here. So angle bracket u sine v, comma, negative u cosine v, comma, v cubed, dotted with the cross product, which we just found, that has components sine v, comma, negative cosine v, comma, u, differential a. Now differential a is equal to du dv, so we have the double integral over the region R of this dot product. So we have du dv. The limits of integration for u are going to be from 0 to 2, also given here. And the limits of integration for v will be from 0 to pi to trace out the region R, also given here. So for the next step, we'll find this dot product and then evaluate the double integral. So for the dot product, we have u sine v times sine v, that's u sine squared v. And then we have plus negative u cosine v times negative cosine v, that's plus u cosine squared v. Then we have v cubed times u, so just plus u v cubed du dv. But notice how for these two terms, again, if we factor out u, we'd have u times the quantity sine squared v plus cosine squared v. So this would simplify to just u times 1. So we finally have the double integral of u plus u v cubed. And now we integrate with respect to u, so we have the integral from 0 to pi of, we'd have u squared divided by 2, or 1/2 u squared, plus u squared divided by 2 times v cubed, that'd be 1/2 u squared v cubed. Performing substitution for u, when u is 2, we have 1/2 times 2 squared plus 1/2 times 2 squared v cubed. And when u is 0, both terms are 0. So simplifying, we get the integral from 0 to pi of, this is just going to be 2, this is going to be 2 v cubed. Now integrating with respect to v, we have 2v plus 2 times v to the 4th divided by 4, that'd be 1/2 v to the 4th. When v equals pi, we have 2 times pi plus 1/2 times pi to the 4th. And when v is 0, both terms are 0. So the exact value of the flux integral is 2 pi, and this would be plus 1/2 pi to the 4th, which is a decimal approximation, is approximately 54.9877. I hope you found this helpful.